Okay, so we are now going to transition into the bread and butter of statistics, which we've been building up. We talked about it a bit last week. What did we talk about last week? Anyone? Types of error. Yeah, absolutely. Tell me more, Daniel. We discussed null hypotheses and whether we reject or fail to reject the null hypothesis, what that looks like. And we didn't really done in types of error, right? So a type 1 error is what? What is the type 1 error? The false positive. Could you elaborate a little bit? Oh, yeah. The type 1 error is when you reject the null, when you should have failed to reject the null. But can either of you give me an example of type 1 error? Since you were going to say the same thing. Michelle, do you want to give me an example of type 1 error? Reading a book that turned out to be terrible. Great example, right? Because what's your null hypothesis for any book that you encounter? What's your null hypothesis? No? What's your default, like, is it you read it or you don't read it? So you read every book that you encounter. You must be very busy. Just constantly read everything you encounter. It's like, I got to read that. You walk into the library, you probably won't be able to leave there for years. Your null hypothesis is you do not read books, right? There's a million books, right? So your null hypothesis is no. Your default is no. And when you decide to read a book that turns out to be bad, you are rejecting your null hypothesis. You are deciding to read the book. When you should have failed to reject it, you should have put it in there, I'm not going to read that. You know, I don't know what you like and what you don't like reading, but I'm not going to read that like book on the history of salt. Right. Which, by the way, there's a great book on the history of salt called Salt, a World History by Mark Kolansky, which I recommend. It was really great. I don't know what kind of books you like reading, Michelle. Apparently you read everything.
I read crime books.
Okay. All right. So the fact that you have a genre, crime books, immediately tells me that you were lying when you were like, I read everything I can find. Right? Just like. Okay. So with that in mind, we then transition to the more mathematical part of this hypothesis testing. Let's imagine I have a machine, and this machine puts ketchup in a bottle. This is not a good ketchup bottle. I don't know, whatever. So it looks like ketchup, just pretend. The machine should put in 400 milliliters of ketchup. It's a big ketchup bottle. It should put in 400 milliliters of ketchup. But if you ever did anything with ketchup, it's a gooey kind of substance. It can get gum up in the works. The machines themselves can sometimes have problems, right? They can break down, they can slowly wear out, they can fall apart. So we want to know if the machine is working properly. How do we figure out if the machine is working properly? The machine is putting in 400 milliliters. We weigh the bottles, right? Do we weigh every single bottle? No, we take a sample. Right? And then from that sample, we get an average. So we take a sample, ideally a simple random sample, just grab a few of the bottles, weigh them with a very precise measuring scale, some sort of measuring tool, and then see, oh, okay, they average this amount. What is our null hypothesis for this machine? What is the null hypothesis? For 400 milliliters. Yeah, so the null hypothesis is, we should get 400 milliliters for an average. What is the alternative hypothesis? It's not 400 milliliters. All right, remember the alternative is everything the null is not. not 400 milliliters. So when we get our sample, let's imagine that our sample average is 402 milliliters. Is there something wrong with the machine? Is there something wrong with the machine?
Within the confidence interval, I mean?
Yeah, it does. It depends exactly if it falls within the confidence interval. Now, granted, and note, by the way, I've got to highlight this. This is a one or two-tail test. Two-tail test. Why does it make sure? Why can we say, Michael, it's a two-tail test?
Because you're saying if it doesn't equal the set of form, it's supposed to be higher one.
Right, exactly. In other words, too much ketchup is a problem, too little ketchup is a problem. So we got 402 milliliters. That seems like it's too much. But you're saying it's more complicated than that?
I mean, there's a random chance that could be normal, or it could just be too much.
Exactly. So Michael is hitting the nail on the head. By random chance, that it just might have been a little large, right? So let me put it this way. Let's build on that. Let's imagine this didn't come out at 402. Let's imagine it came out at like 500 milliliters. It's supposed to put 400 milliliters. It's putting in 500 milliliters. Is that random chance? No. So probably it could be, but probably not. Right? So one of the things that we're trying to figure out, and this is essentially what we're talking about today, hypothesis testing. The big thing we're trying to figure out is this number that's different than an average, is that due to random chance, or is that due to some genuine difference? There's some genuine problem. And one of the things that will make a difference here, things that matter, what's the difference in means? You know, we have two means here. We have what it should be, the population mean, and then we have a sample mean. And so one of the things that matter is, what is that difference we're talking about between these two means? 2. Well, let's imagine we have 402 milliliters, so it's a pretty small difference. But let's imagine that 402 milliliters is based off of, I don't know, like 6,000 bottles. That we pulled 6,000 bottles and measured exactly, 6,000 of these bottles with a very exact tool, and we got 402. The fact that we pulled 6,000 rather than, say, 5 or 6, does that make it more likely or less likely that this difference is a genuine difference? That there's something wrong with the machine? More likely. Why? Why do you say that? If I pulled in 6, central limit theorem, right? Law of large numbers. That's probably, it could be large just by random reasons. If I pulled in 6,000, is that going to be large by random reasons? Probably not, right? The chance that I would get a bigger than 400, so over and over, so much so that this brings it up, the overall average is 402. That's a pretty small chance. Right? When I'm working with 6,000, that's a lot less likely than when I'm working with 6. Remember, no sample is perfectly precise, but some samples are more precise than others. Right? So we have to think about not just what's the difference in the means, but how many observations am I using? What am I basing this difference on? Observations. Similarly, what if this just isn't a very well-built machine? What if, it's supposed to put in 400, but pretty regularly it might put in 404, it might put in 396. It's just not very precise. Is this more or less likely to be a random result? More, why? Yeah. Like, if this was like way outside its normal parameters, then sure, it's probably weird. But the fact that this thing fluctuates so much by itself when it's working properly tells me that, if I get 402, it's probably just working properly, right? It's just a really weird, terribly built machine. Well, maybe it's really good. We don't know what year we're working in here. So the other thing I'm concerned about is what is the natural dispersion of the population. These three things directly then influence our conclusion on if we should reject our null hypothesis and go with our alternative, or fail to reject our null hypothesis. And we use these bits of information. We're going to put it into an equation, and then we're going to output a number. And then we're going to compare that number with a threshold, a critical value. And that will determine if the result is statistically significant or not. Are we good so far? Any questions? Okay. I'm going to give you the equation. Get this. Let's start off here. We are using a z-score. We are using a z-score because I am going to assume I know sigma. What is sigma? Well, in this example, I know sigma. I'll give you sigma in a moment, but what is sigma? What does that represent? Yeah? Population standard deviation, exactly. So in other words, we know exactly what the dispersion of the population is. Right? If we don't know sigma, we have to rely on our sample standard deviation, which is our estimation of this. And we use t. But because we know sigma, we know z. We are also going to take the absolute value. I'm going to erase this part right here. I don't think I need this right now. We are taking the absolute value because this equation essentially turns this raw information we'll have, like, we have a mu here of 400. We will have an n. We will have a sigma. And it takes these information and it's going to turn into a z-score. And this z-score is a reference to our standard normal distribution with a mean of 0 and a standard deviation of 1. We call what percent of observations are within 1.96 standard deviations of the mean? What percent of observations? It's not a 4, that's a +1. What percent of observations are here? 95. In other words, we're going to get a z-score. If that z-score is within this confidence interval, in other words, if that z-score is less than 1.96, then we will fail to reject the null hypothesis. It's probably random. There's a 95% chance that this result of 402 is random. If, on the other hand, it's greater than 1.96, then it's probably not random. And we will reject the null hypothesis and we will claim statistical significance. But this is why we take the absolute value, because the absolute value is all about distance. We don't care if it's really far away from 0 in this direction or if it's really far away from 0 in this direction. We're just going to turn everything positive. Both the critical values will always be positive, 1.96 or 2.326 or whatever it is, and our z values will always be positive. Just makes things easier. Next, we're going to take this difference in the means and we're going to put it up here, x bar minus the mu from our null hypothesis. That HO is, of course, the symbol for the null hypothesis. It's just referencing that's where that mu comes from. I can even throw it in here if you want, just for boosting those. Note, the larger this is, the bigger Z is. The bigger Z is, the farther all things will get to zero, and the more likely that this gap between what we're observing and what should be is not random. We are now going to throw in our friend sigma. Again, sigma is our dispersion. So the bigger this value is, the more dispersed it is, then the lower this value is, Z is. Because if this gets larger, then there's a greater likelihood that we just got a larger number or a smaller number just by random chance, because it naturally fluctuates more. And then finally, we take the square root of n, which is how many observations I have. Same story, as n gets bigger, then Z gets bigger because we have more information. 6 isn't as informative as 6,000. Sarah, how many ketchup bottles do you want to grab for our experiment? How many ketchup bottles do you want to grab?
1,000.
Okay, 1,000 is too many. Do you really want to measure 1,000 bottles just to see if this machine works? Okay, we can do 20. 20 is big, but 20 is doable. Let's imagine we pull 20.
This stuff is pulling 20, that's
Okay. So let's imagine it's 3.6, but I'm sorry, the n is 20, and let's imagine that the standard deviation, the population standard deviation is 3.6. These 4 numbers in any problem you encounter will be given to you. Now, here are the steps to doing hypothesis testing. 1, are you using the t-score or the z-score? If it's t, you know, if it's z, you know sigma. If it's t, you don't know sigma, and you have to rely on s, the estimation of it from the sample. 2. Is it 1 or 2 tails? Is this a 1 or a 2-tail test? It's a 2-tail test, right? Why do you know it's a 2-tail test?
Because when the values multiple.
Yeah. In other words, the machine isn't working properly if it's putting too little ketchup in. But it's also not working properly if it's putting too much in. So either one is bad. We're testing for unusualness, and that is a 2-tail test. Three. Level of confidence. So typically this is given to you, or this is typically in any sort of exam question, this will be explicitly asked. But for your perspective, this matters too, because this is something that's kind of arbitrary. Like, if this machine is a real pain in the ass to fix, or if this machine is a real pain in the ass to clean, and it takes hours and hours and hours to do so, and during that time it can't be putting ketchup in a bottle, then we might want to be only really sure that this is a problem before we shut down production. So we might demand a very high confidence level, say 99.9. If, on the other hand, it's a relatively simple thing to fix, then we might just establish a low threshold of, say, 95%. So that level of confidence, it's typically in a problem, it's typically requested, just say 99, at 95% confidence, at 99% confidence, what you should conclude, and this is typically good. Step 4. Calculate your Z or T value. For example, because we know our sigma, we will use Z. I'm going to actually do it this way. T right here, Z over here. Because then it matches. 5. Using the confidence level, if it's a 1 or 2 channel test, or if it's a T or Z, determine the critical value. I'm giving you very detailed steps. A lot of this is pretty straightforward, especially when you do it a lot. I'm giving you very detailed steps just to show you all the things you're thinking about. And finally, 6, compare. If your calculated value is greater than your critical value, then it is statistically significant. And you reject the null hypothesis. If the calculated value is less than the critical value, then it is not statistically significant. And you fail to reject the null hypothesis. This is hypothesis testing in 6 easy steps. And that covers the bulk of the counting hypothesis. There's a little bit, I think we'll fill up time, hopefully we'll have time, we'll talk about hypothesis testing with proportions. But then that's just basically the same steps, just use a different equation. Let's figure out this is the case. Let's go through an example. I don't know what that 0 is doing. Let's get rid of that 0. There we go. Now, I have to warn you, Excel does not have that equation built into it. It does not have that equation built into it. You have to do that yourself. First, let's make a list of all the information we care about. So we care about mu, and we care about x bar, and we care about sigma, and we care about n. Now, what I like to do with equations like this, just to show you all the steps, is I'm going to divide the numerator and denominator, and I'm just going to indicate them into 2 different cells, and then I'll have a third cell that's the result. So I'll have a numerator, I'll have a denominator, and then there's my calculated value. And we can just work backwards. The calculated value, again, is all about what? Begins with a D. Distance. All right. So remember, this is all about how far away we are from 0 on a standard normal distribution. So we take absolute value. The equation for absolute value in Excel is simple enough. It's just ABS. And we're going to be taking that numerator divided by that denominator. The denominator is just sigma divided by, we need to do the square root. Does anyone know what the square root is for Excel? What's that function? SQRT. And so we're going to be referencing n. Miranda, what do you think we should put up in the numerator? We have x bar minus mu, right? So same thing, right? Again, that subheading, that HO subheading, or subscript, I should say, that HO subscript is just a reference to the null hypothesis. It's reminding us that mu is derived from the null hypothesis. It's our baseline for comparison. So B2 minus B1. I don't know why that switched to percent. Let's just get rid of that. There we go. Make sure I don't want any of these to be percent. Oh, they're all general. There we go. And then we just put it in, and it'll calculate it for us. So our mu is 400. Our x bar is 402. What's our sigma again? Absolutely. So 3.6. And then we are working with a sample of 20. We get a result of 2.48. What can we conclude about that 2.48? What does that mean? Go back to the list of the things we care about. We calculated our t-value, we got a z-value, right? We know it was a t-score. It's a two-tailed test. We have the top level of confidence, so we're going to do that now. We need to determine our critical value. So let's imagine it's 95% confidence. What is our critical value? 95% confidence, two tails, z. 1.96. Where'd you get 1.96 from? Yep. According to that table we have, right? If you didn't want to look it up, you can always just have Excel look it up for you, right? We talked about this. You can just say, hey, Excel, I want to know what it is for, let's do absolute value, for norm invert, and I want to do a two-tailed test. So alpha divided by 2 is, what's the alpha for 95%? Hold on, I wanted to do this standard. That makes things a little easier. I'm sorry, what? Divided by 2? So you're right. So alpha for 95% is 0.05. We divide it by 2. We get 0.025. Oh, and I forgot. There we go. And we get 1.96. So if you ever want to know what a critical value is, you can just put it in. In fact, if you want, you could have done, if you didn't want to do that math, 0.05 divided by 2. You could have done that too. So, in fact, oh, we could even make let's do the whole thing. Oh, that'll be fun. You guys were like that. You're just so excited. Just don't talk all at once. So we could have, this is 95% because this is the alpha. And then we can just reference. There we go. There are critical values. Again, I never would have you memorize those critical values because A, they can be looked up any number of places, and B, you can always just pull them up on Excel. But it's nice, like if you don't have those critical values in front of you, especially if you want to show off a little bit, you can just use Excel to figure them out yourself. And what's cool is now we're not constrained by those. If you want to know what it was for 98 confidence level, or 92 for some reason, or 96 or whatever, you can figure it out. So, is this 402, is that statistically significant? Is that a statistically significant result? Yeah. Well, yeah. I think I said 95 at first. No, 95. Is it not? Is 95? Is it statistically significant at 95% confidence? Yes. How do you know? Exactly. We got about 2.48. It is bigger than 1.96. It is statistically significant at 95. Is it statistically significant at 99%? No. How do you know? It's less than, right? We have a critical value of 2.576. It is less than that, because it's only 2.48. It is not statistically significant. And if it's not statistically significant here at 99, or alpha 0.01, then by definition, it is also not statistically significant here. Because if it's less than this value, since this value is larger, it's going to be less than this one. Any questions? Yeah?
So does that mean at 95 critical confidence level we reject
Absolutely. At 95% confidence level, we would reject our null hypothesis and say, hey, there's something weird with the machine. Say 99%, we would fail to reject the null hypothesis. The machine's probably working fine, right? This is a little bit of the judgment with stats. We don't, it's all about probabilities. It's all about estimation. It's about judgment. But it helps us organize our thoughts on how we should be approaching these numbers. Because without this framework, we get 402, and we're like, is that random or not? I have no earthly idea, right? Now we have something to help figure that out. Now we have some system in place. Does anyone have any questions? Yeah, Sarah. So mu is our pre-existing standard, right? I gave that to you. I said, this machine is supposed to put in 400 milliliters. So that's sort of like what we're judging at everything against. Any other questions? Okay. Let's do another one. So let's imagine it typically takes an average of 10 minutes for someone to run a mile. Now, we developed this really amazing sports drink that we want to say improves performance. So we need to obviously test it because we don't want to get like arrested, or not arrested, fined for false advertising. So we have this sports drink and we are going to give it to some athletes. They're going to drink it and they're going to see how fast it takes them to run a mile on average. Let's imagine we give it to 16 people. Not athletes, just people, just regular people. And they run, it only takes them 8.75 minutes to run a mile. That seems like it's faster, right? That seems like it's an improvement, right? But is it a genuine improvement? Is it something that is probably not random? Or is it something that might truly be random? Now, in order to figure this out, I need to know one more piece of information. What is that random piece of information I need? Sigma, exactly. So Marvin has correctly identified we need sigma, or at least some estimation of sigma. Let's say let's suppose we know sigma. Let's suppose sigma is 2. So it takes 10 people, it takes the average person 10 minutes to run a mile with this population standard deviation of 2. And then we're going to give this drink to 16 people, and then they run, and it only takes them 8 3/4 minutes. Is this a 1 or a 2-tailed test? Exactly. It's 1 because I'm trying to find for improvement. I'm giving people this sports drink. Therefore, I want them to be able to run faster. What would be our null hypothesis here? What's our null hypothesis? It's not. And there are two ways to make it not an improvement. What are those two ways? The same or worse. While the alternative hypothesis is better. And note, in this case, because we're talking about running speed, greater values are worse. Right? If it takes you 12 minutes to run a mile, that is worse time than taking 10 minutes. Right? Lower numbers are better. Golf is the same way. So don't immediately assume that more is better. Sometimes less is better. More sales are better, but fewer golf strokes are better. Right? More visits to your website are better, but fewer complaints are better. So you have to really look at the context to figure out what is null hypothesis and what is not. Okay. So all we really have to do now that we know it's a one-tailed test, we'll talk about level of confidence in a moment. And let's work with, let's see, we have, what you can actually help me out. What is my mu? What is my mu? 10 miles, 10 minutes. 10 minutes. Yep. What else? What's my X bar? 8.75. Yep. What's next? 2. And then how many people do I have? 16. So we have a calculated value of 2.5. Is this statistically significant? What are these values for right here? Because 1.96, 2.576, and 3.291 are critical values for two-tailed tests. This isn't a two-tailed test, though. This is a one-tailed test. Right? So we need to get our, if that's two tails, let's get our one tails, or one tail. So there's a couple of ways to do this. You can just look it up, or you can just copy and paste here and then remove that divide by 2. Because we are no longer taking alpha divided by 2, we're just taking alpha. That's what a one-tailed test is. Ooh, and let's there we go. And boom. And there's our one-tail values. Is this statistically significant at 95% confidence? 2.5 is greater than 1.645. Is it statistically significant at 99%?
No.
Yes. All right, how do you know? It's still greater than 2.326. 2. Yep. What about 99.9? Right, exactly. Not quite large enough. So this value, note that we got a similar value. We got around 2.5 each time. But because we are working with a one-tail test, the threshold is lower. The statistical significance is lower. Yeah, Destiny. Yep, absolutely. Except now I got to scroll over. Ooh, we don't really need that C, do we? We don't really need that C. And we can shrink this down a little bit. And we can expand this. And let's do that. Let's do that. There we go. Any questions on this? If it turned out I was just checking to see if things were unusual or not, if I was doing some sort of unusualness check, then the standard that I have is higher for statistical significance, and then I won't be able to claim statistical significance at 99. So because by definition a test of improvement only concerns itself with one of the tails, then that means all of that alpha is concentrated on one side and that area extends outward, and thus the distance between that boundary and 0 is smaller. And so that the threshold is always lower for improvements. Any questions? Okay. Let's screw around a bit. Because in practice, you don't always know the population standard deviation. Sometimes you have to rely on just the sample standard deviation. And so the sample standard deviation uses a slightly different equation. We use T instead of Z because we are using the student T-score. X bar minus mu sub HO S instead of sigma. But you can see it is, for all practical purposes, exactly the same. For all practical purposes, it is exactly the same. To show you how big of a difference switching from Z to T makes, let's assume that our estimation of sigma S is the same. So in other words, our sample standard deviation is also 2. So I will change the sigma to an S, and we will have the same mathematical result. What is different is our thresholds change, our critical values change, because these right here are Z-scores, but I need to use T-scores. I'm going to show you how to do it for T and Z. We obviously, for this problem, only need it for one tail. I'm sorry, I'm going to show it to you for 2 tail and 1 tail. We obviously, for this problem, only need it for 1 tail, but it can come up in both ways. How do we figure out what the T-score is? I will give you a hint. How do we figure it out here? What did we use? Anyone? Exactly. Well, we don't have there's no S there, but yeah. So we're going to start with absolute value because otherwise it's going to be negative. I mean, it won't matter for T, for 2 tails, but for 1 tail it will. And then we will have T dot invert, 2 tails. And that probability, hold on, that's 0.5, it just doesn't look that way. Comma, what are our degrees of freedom? In this example, what are our degrees of freedom? 15, right? Or 16 minus 1. And let's remember to put in those locked cell references because we will be using that again. Oops, and it's going to say missing an argument in the parentheses. No, it's fine. Degrees of freedom. It's fine. There. It didn't like the fact that I was missing a parentheses. And that's our critical values for 2 tails. Note how much larger these values are to these values. Because we have less information, we're working with only 16 observations. That means we only have 15 degrees of freedom. And so therefore, our threshold for statistical significance increases. I'll show you the formula. Again, I put in the ABS there. I didn't really need to, but I put it in there to harmonize it with the other ones because I think that looks better. And I'm certainly going to need it for the T invert with 1 tail because that will end up being negative. It's confusing when you throw negative numbers into this. Any questions so far? Again, what we are doing is we are essentially taking a table that stat students used to have to rely a whole bunch on, but Excel has it all built in, and we can just do it basically automatically. So here I am doing the same thing for one tail. You know what the only difference is? I removed the .2t option because, again, it's a two-tail, it's a one-tail threshold, not a two-tail threshold. And then I can just copy and paste that down, and then it's going to remove my cool border, so I'm just going to put my border back in. And I want my, there we go. You can shrink this in a little bit. Any questions? I'll make this look all pretty while you figure things out. Let's bold that, so it's clear. Here's our alphas. Ooh, we can do that. We can do alpha. Ooh, and let's do that as well. And then we'll make that. Ooh, and let's do a border out here. Ooh, and let's do a border. I can just fiddle with this all day while you guys are figuring out if you have any questions. There we go. So, okay. So you can tell me, is this statistically significant? Now that we switched from sigma to S, is this still statistically significant at the 99% level? Anyone? No, it's not. Wait, how do you know?
Because this is only 5, is below.
So,
99% threshold is 2.6.
yes, but technically now it's a t-score. Yeah. So our exactly. So our calculated t-score 2.5 is now not quite large enough for the 2.6 threshold we have. It is no longer statistically significant at 99% confidence. What's neat about this is that because of the way we set this up, I can change n, say, let's look at 17 or 18 people, and you will note that not only will our calculated value increase, but our critical t values will decrease because we'll have more degrees of freedom. So if I go to 17, for example, that is no longer 2.5, that is 2.57, and that is no longer 2.6, that is 2.58. It's closer. If I go to 18, all right, now it's 2.65 versus 2.57. Now it's statistically significant. Right? Sample size is super important. Getting a bigger sample size is really great, especially if you're working with the t-distribution, because it will not only improve your calculated t-value, it will, increase your calculated t-value, it will also reduce your critical t-value. And thus you're more likely, if there is statistical significance, you're more likely to find it. If you increase your sample size, it not only will increase your calculated value for a t, it will also decrease your critical t values. And so therefore, you are more likely to get statistical significance. Not that getting statistical significance is inherently good or inherently bad, it's not, but it really highlights how important n is in these cases. And in case you're curious too, just as a reminder, if we put in like 50,000 for n, you see that our t values are just like our z values because you have so many degrees of freedom. They are functionally the same, right? If you're trying to estimate your sample standard deviation, the population standard deviation with like 50,000 observations, you probably just have the population, right? It's just a very good estimation. And then you get a calculated value of 139. Let's go back to, any questions? This works really great for things like of clear values where there's no bounds. But just as the proportion confidence interval has its own equation, the proportion z-stat for hypothesis testing has its own equation. It still uses z, so you'll still use these z values right here, but you use a different equation. We still take the absolute value. We still take p bar minus the population value, but we don't call it mu, we call it pi. So this is our sample average just as before, this is our population average. And then you take pi, 1 minus pi, divided by n, square root thereof, and that gives you a z-score between these two. So we'll note how similar they are, for one, but this p bar is the proportion sample average. This pi is the proportion population average. And the n is still n, and these are still pi's. And so this is pi 1 minus pi divided by n, and that's our sigma essential. So, any other questions? Okay, let's do an example. I need a new thing. So we have p bar is what we care about. I think, how did I do this here? I started with mu. Okay, so I'll start with pi, I'll start with p bar, and I'll start with n. Our numerator is going to be, just as before, the difference between p bar and pi. Again, pi is not 3.14159. Our numerator, our denominator, is, and this is where it gets fun, be very careful about order of operations. Keep track of your parentheses. This is not built into Excel. You have to do this yourself. We are going to take the square root of pi times 1 minus pi divided by n, and we close our parentheses. And then, of course, for the calculated value, we'll just take the absolute value of the numerator divided by the denominator, as per usual. All right, I got 2 minutes left. Any questions so far before we move forward? Yeah. Yeah. There's a lot going on in the denominator. And while you're taking a look at that, I will give you the scenario. So, suppose you work at a growing trucking company, and you want to know how its recent expansion has affected the business's operations. Because one of the problems, of course, is that when you get big, maybe the quality of the service goes down. It's hard to manage lots of things. So let's imagine before the expansion, 20% of deliveries were late to their destination. And after the expansion, 28% of deliveries are late. Is this a statistically significant difference? Is this a warning sign? Now, keep in mind that 28% of deliveries that are late is based off of 100 deliveries. It's based off of 100 deliveries. So, what do? What's pi in this case? Yep, so 20% of deliveries were, so do I put it as 20? 0.2. Do not put it as 20. What happens if you put it as 20? You are going to get an imaginary number, because right here, you'll be taking 1 minus 20, which is a negative value, and then you'll be taking the square root of it. Oh, you don't want to do that. So yeah, make sure it's 0.2, 20%. Our P bar is 28% are now late, so I'll do 0.28. And again, this is out of 100 deliveries. That P bar is derived from 100 deliveries. And because I made these numbers nice and clean, we get 2. Statistically significant at 95%, not statistically significant anywhere else. Well, actually, wait. I have to be careful, don't I? Is this a 1 or a 2-tail test? 1-tail test. Statistically significant here, still not statistically significant at 99%. Right, with that 2.326. But not bad. A lot closer anyway. And note if I increase this, like let's imagine well, maybe this persists after 200 deliveries. Now we're getting into territory where now it is statistically significant at a 99%. And now that is statistically significant. We do 144, we get a nice clean number because that's 12. All right, any questions? I'll show the formulas here, just in case people are curious, and I will let you go.